Welcome to the video for Lecture 22, Section 2. This video continues the presentation on second-order systems and the equations used to describe them. In this video we will talk about the second-order response to impulse inputs and introduce transient response terminology and definitions. In the previous video I showed the equations for second-order processes and the responses to a step change input function. In this video we will look at the equations and the responses to impulses. Here is the second-order transfer function. The output function is y and the input function is x. In the previous video we used a unit step change, so x of s equaled 1 over s. This time we are going to say that our second-order system experiences a unit impulse. This means that the input function x of s is equal to 1. We get this from equation 4 in the Laplace transform table. Here is the Laplace domain expression for a second-order system that experiences a unit impulse. Note that the last term needs to be a 1 for us to use delta to describe the characteristic response. As we did when we had the step change input, we will have three cases: underdamped when delta is between 0 and 1, critically damped when delta equals 1, and overdamped when delta is greater than 1. Here is the first case. Delta is between 0 and 1 and the response is underdamped. Here is the time-dependent equation for a second-order process experiencing a unit impulse. Note that the final value theorem value is 0 as time t approaches infinity. This slide shows a plot of y of t for the underdamped case for a second-order process in response to a unit impulse input. As before, the underdamped response overshoots the final value and commonly has multiple oscillations around the final long-term value, which is 0 for the unit impulse. A well-behaved response will settle down fairly quickly. Well-behaved underdamped responses can be a good response. This graph shows a typical response for an underdamped second-order process to a unit impulse in the input, and the response is called underdamped when the delta is between 0 and 1. Here is the second case when delta equals 1. This is the critically damped case. The slide shows both the equation and a graph of the response. The critically damped response of a second-order process subjected to a unit impulse input produces the lowest overshoot, no oscillations around the final value, and reaches the final value sooner than overdamped responses. Here are the results for the third case when delta is greater than 1. This is called the overdamped case. Similar to the critically damped case, there is one overshoot, no oscillations around the final value, 0 in this case, and the critically damped response is sluggish relative to the critically damped response. Here is a plot of the three second-order responses subjected to a unit impulse. The underdamped response has oscillations. The critically damped one has one overshoot, no oscillation, and reaches the final value sooner than the overdamped response. The overdamped response has a single overshoot, no oscillations like the critically damped response, but is much slower. As before, if we use an impulse of magnitude a rather than a unit impulse, the results are simply multiplied by the value a. The purpose of all this process control work is to be able to estimate how a system will respond to different process inputs, such as step changes, ramps, and impulses. As the overall transfer functions become more complex, we produce higher-order equations and dynamic responses, as we have just done for second-order processes. Now is a good time to define some of the terms we use to describe transient responses. First, let's talk about overshoot. I have used the term overshoot in this and the previous video. Overshoot describes the fact that the response goes over the final value. The maximum overshoot occurs during the first overshoot and is the difference between the maximum response value for y and the final value of y. The graph shown is for a unit step change, so the final value of y is 1. The graph indicates that the maximum value of y is a little over 1.8. So the maximum overshoot is approximately 0.82. This is an excessive overshoot. Later, when we discuss controller tuning, we will say that we typically want the maximum overshoot to be 0.025 times the final value. We can also calculate the percent overshoot using the equation shown. Please note that the overshoot can be negative, So if we had a negative step change to a second order system, the final value would be negative, and if the system was underdamped, the response would have a negative overshoot. Another transient response term is the rise time. This is the amount of time between time t equals 0 and when the response value y crosses the final value the first time. Depending on the system and the response, the rise time can be very small or fairly large. Response time or settling time is another transient response term. The response time describes how long or how much time it takes for the system response to settle down so that the response y of t is always within some response tolerance. So if you want the process output to be within plus or minus 5% of the final value, then you can calculate a range within which you are satisfied that the process is operating within normal tolerance limits. You can give the tolerance values in similar terms as the uncertainty values we used with measurements, plus or minus some amount. This last technique is important when subjecting the system to an impulse when the final value would equal 0, as we did earlier in this video. So if given a graph of the process output response, we draw on the tolerance lines and find when the output consistently stays within the tolerance lines. For the graph shown, it is about 4.5 times tau. Another term commonly used to describe how an underdamped transient response is performing is called the decay ratio. The decay ratio is the ratio of successive overshoot peaks. For the figure shown, the ratio is roughly 0.19 over 0.82. The ratio is about 0.15. This is not a good decay ratio. Decay ratios are typically between 0.4 and 0.8. Smaller values, as shown here, lead to excessive overshoot. The 0.82 is an excessive overshoot. Larger decay ratios lead to sluggish responses. As with many engineering problems, there are trade-offs associated with transient response specifications. You need to balance speed versus damping. If you want lots of speed, you will probably have large overshoot. This balance is achieved by keeping delta between 0.4 and 0.8. Larger deltas lead to sluggish responses, which means that your output is not within your specified tolerance limits for a longer period of time. If you have smaller delta values, you have excessive overshoot. A fast rise time indicates a fast response to the changing process input, and a fast response usually leads to larger overshoot. You cannot have small overshoot and a fast rise time. This brings me to the end of the Lecture 23 Section 2 video. Write down any questions you have and bring them up in class.